let me go back and I want to show you something. Last class, I had posted an Excel spreadsheet. All right. Yeah, not everybody is here. I wonder why. All right. So all of you can see this, right? You can see this series, 1992 up to 1999. Yes, you can see that, everybody?
Yes.
Okay. So let us think, Roxolana, let's think that this is this y sub I. And because I don't want to mess with the equation editor, when I write y sub I like this, it should be like this I should be the subscript, okay? And and it will be t. So when t equals 1, 1992, the return is 4%. When t equals 2, the return is 3%, and so on and so forth. Obviously, I can go from 1990, I can keep going, okay, up to long time series. But I just want to just use this simple time series to ask you. So this could be a return on IBM from 1992 to 1999. Now, the question is this. Each of these numbers, in 1992, it was 4%. In 1993, it was 3%. I mean, where did they come from? And all these numbers, 4, 3, 2, 3. I mean, why not 6 here in 1993? Why not 10 in 1994? Why not 5? So the return in 1992, this 4, this 1992 here, you can say this 1992 is x sub t, x, or sorry, it's y sub t, y sub t, y 1992, okay, like that. This y 1992 itself is a random variable. Just that return in 1992 is a random variable. What is the definition of a random variable? Again, today I'm giving you a big picture. So just don't worry if I'm not doing R programming and all that. Now, a random variable is like, it's an item that can take different values with different probabilities. That's what a random variable is. A random variable is like height. If you come to this class, you know, you're 6 feet, she's 6 feet 2, he's 6 feet 4, she's 5 feet 9, he's 5 feet 6. So the same height, there are different realizations of height. So there's 6 feet, there's this, there's 5 feet, 5 feet 8. So the return in 1992 itself is a random variable. Why? Because the return in 1992, what numbers can the return take? Does anybody know? What numbers? What are the possible numbers for the returns? Exactly. So this variable itself can go for minus infinity to plus infinity. Just this, only this one. We happen to observe one particular, from minus infinity to plus infinity. How many possibilities are there? Infinite possibilities. This number 4 happens just to be one of those infinite possibilities. So the return in 1992 could be infinite possibilities, but we just happen to observe one of them. That's 4. What other variable is there? Anyone tell me? What other variable?
The time series?
993.
Why
94.
the return in 1993 itself is a random variable. Are you following this?
Yes.
Yes.
Okay.
Yes.
What possible numbers? What possible numbers can the return in 1993 take? From minus infinity to plus infinity?
Yes.
Are you with me? So how about what other random variable do we have? This 19. Okay, this is by itself, it's a random variable. But we happen to observe this time only two, this only one possibility, two, out of
Babe, show me your
a
phone.
gazillion, an infinite possibility.
What you're doing, chat.
Okay, so here we have random variable, random variable, random variable, random variable, random variable. We just happen to, for each random variable, we just happen to observe 6 here. 6 is one possibility out of infinity. 4 is one possibility out of infinity for 1998. Are you with me? Now, all of this, let me copy. Please bear with me, okay? Because many of you are asking me questions, and it's just my fault that I have not been able to. No. What do I want to do? I want to write y here, this y here.
I think, Professor, if you select Y 1992 through 1994,
Okay. Thank you.
and then you extend it,
okay,
it will autofill.
Oh my God, you guys are just
no, just extend it on the no.
Here.
Yeah, right there. Yeah.
Just extend it down.
Yeah, you should autofill.
Extra credit.
No.
Okay, thank you.
No, it didn't.
No, so no, it's okay. It's okay. Now I can change each of them, right? 1994, 1995. It's okay. It's okay. Thank you. And I can change it to 19. Everybody, please bear with me, okay? 96. Somebody is missing here. Is Mr. Murphy here? My man. He will normally chat with me to say he's here. Okay, so in this example, how many random variables do we have? Anybody take a wild guess?
7 or 8?
8.
8.
We have 8 random variables. Is that right?
Yeah.
And so what is this number? This number is just one number out of infinite for this first random variable. This number is just one number out of infinite for this variable. So each of these numbers is just one realization of infinite for this random variable. This whole combination is what we call stochastic process. This entire thing is what we call a stochastic process. And these numbers is just one realization of a stochastic process. That's why we use the idea of a joint distribution, because this one here has its own distribution. This one here has its own distribution. This one here has its own distribution. This could be normal. This could be t. This could be chi-square. I mean, this could be different distributions. So when you do your homework, what you are trying to see is this line of numbers from 4, 3, 2, all of this is one realization of a joint distribution of all these random variables of the stochastic process. Okay, it's very important you understand that. Think about it. It's a very this is a very deep concept. Keep thinking about it and ask me questions. Okay, later. It doesn't have to be today.
That?
Yes, Joseph.
Could you repeat that about that they like on the homework? What we're trying to figure out about.
Okay,
that.
for the homework, I asked you these numbers, this series. Huh?
Yeah.
Do they come from a normal distribution? That's what we do with Jacques Berra.
Okay.
Essentially, what I'm asking you is this is a joint distribution. This is a distribution not of one variable. It's a distribution of many variables together. That's why we call it a multivariate distribution. Okay, that's the theory behind this. So
okay.
these numbers 4, 3, 2, 2 is just one. We observe the realizations of these 8 variables together at one time. Okay, so that's what we're doing. So when I ask you to test Jacques Berra, I'm saying these numbers, are they all from a multivariate distribution, multiple variable distribution? 8 variable distribution working together. That's what we call a joint distribution. Okay, good. It's okay. If you don't get it, I'll keep talking about it until we get it in this class. All right. So let me move, let me remove all of this. Let me cut and let me paste. Yeah. So it will not
Wasn't
distort.
it the Leung box, the joint distribution, Professor?
No,
Or
no,
the
no,
box
no, I'm
used?
not talking about, no, you use the long box when you want to test whether their autocorrelation functions are jointly zero.
Yes, yes,
Okay, yes. But so when we do the long box, we're asking
about hypothesis testing, right?
yes, yes, but we're asking, are the ACFs jointly zero? Why jointly? Because there are eight random variables together here, acting together. That's why we say jointly. Okay. So that's a great question you asked. So it's applicable to that. But the long box, we're specifically testing the autocorrelations. Okay. All right. So now let me come to the business of today. Now, the question I want to ask, so when we ask, what is generating these numbers? 4, 3. So it's like, look, I give you a bowl with many, many balls in the bowl, you know, like ping pong balls, different colors. And I say, close your eyes, and you dip. Yeah. So suppose I put eight balls in a bowl. Or no, not 8 balls. Let's say 8. What do you, 8? You know what a die is? Die, D-I-E, right? 8 dice with number 1, 2, 3, 4, 5, 6 on each die. Is that right? You know what I'm talking about?
Yes.
Okay. Suppose I put one of them. It has many numbers, and I put another one. It has many numbers, and I put 8 of them. Okay, and I shake the container, and I ask you put your hand in there and collect all 8 at once, and then turn upside down, and let's read the numbers on the surface. Are you with me so far?
Yes.
The numbers could be 4, 3, 2, 3, 2, 2, 4, 6. Are you with me so far? It could be these numbers.
Yes.
And then when you put them back and you reshuffle the bowl and you grab all 8 at once and you turn them up like this, the chances are the sequence of numbers will be different from this sequence of numbers. You agree, right?
Yes.
Okay.
Yes.
So what we're doing is, okay, instead of picking all 8 of them, if you pick only one, the number could be 4. But if you return it and pick it up again, that number instead of 4 could be 5, could be 2, could be 1. So each die, each of them is a random variable itself. You understand? Yes or no?
Yes.
Makes
Understood.
sense.
Yes.
Okay. Look, think of this. This is my candy that I was just playing with, shoving into my mouth before class. You guys see this, right? This is like a die. Yes, you see that? You see, it's like a die. It has many sides, right? If you number the sides, 1, 2, 3, 4, 5, 6, it has 6 sides. 1, 2, 3. Let's say it has 6 sides. You number, so only this one. If I put it on a bowl and ask you to pick it up, you pick it up and show me the number, it could be 4 right here. This one, it could be 4. And I ask you to drop it again. You know, I drop it and I ask you to pick. You pick it up again. The same die could be, the number could be 3. I put it back again. The same die, you pick it up. The number could be 1. So this die itself is a random variable whose anytime you pick it, it can give you a different number. Are you with me? So you can think of this die as the return in 1992. Now, if I introduce another die, another one, so now there are 2. If you pick up this second one, it can have different numbers: 3, 4, 2, 1, 5. So now I have 2 random variables. If I put two of them together on a bowl, right, and I ask you to pick 2 of them at the same time and show me their numbers, the combination could be 4 and 3. You agree?
Yes,
Okay.
that could be.
Okay. So what I'm trying to say is they all of them together. We call them together. We call it a stochastic process. All right. Now we always like to know what generates the numbers for a stochastic process. All these numbers together like this. What generates these numbers for this stochastic process that combines all 8 of them? We like to know. Now, it might be that you can think of this as just a series of machines, or you as the generator. You put your hand, you grab all 8 of them, you look. We have all these numbers at once for the 8. And then I put them back, I shuffle, you grab them again, I look, another set of numbers. And then another set of, okay? If you are doing it randomly, then this sequence of numbers will be random. Yes? Please tell me you understand what I'm saying.
Yes.
Okay.
Independently distributed.
No, not yet. Not yet.
Okay.
Not yet. They are random. And then if we give it another structure, we make it IID, meaning they are identically independent and identically IID distributed, meaning that, look, this 4 here has nothing to do with this 3. The fact that for 1992, this variable took a number 4 has nothing to do with the fact that 1993 return is 3. Has nothing to do, the fact that this is 3 has nothing to do with the fact that this is 2. The fact that this is 2 has nothing to do with the fact that this is 3. If that is so, we say this whole sequence is a white noise process. It's just like an error term in your regression in Echo 4000. It's a white noise process, meaning, look, what happened this winter has nothing to do with what happened last winter. What happened last winter has nothing to do with what happened 2 winters ago, and so on and so forth. They are totally unrelated. That's a white noise process.
I have a quick question.
Yes, sounds like Roxolana.
That's Lily here.
Lily!
We get us mixed up sometimes.
Yes.
So my question basically is, so are we considering that these are like returns, like stock price returns? And if so, is that considered random? Like would
Prices can be random, returns can be random. Sales of IBM computers in dollars year by year can be random. The number of students that enroll, total number of students that enroll at Baruch College every year, year by year for the past, could be random. It doesn't have to be only returns that can be random. You see, Lily?
Yes, I understand. I was just wondering, like, okay, that makes sense.
Okay, so any series of numbers can be random. When we say they are random, it means they are randomly generated. You see, who is generating them? You, Lily. When you pick all of them together, and then you shuffle, and then you pick, and you shuffle. But if you pick first time and you put them back, and you do not shuffle the cards, or you do not shuffle the deck, then your next pick, the numbers could follow because of what you did the previous time. You agree with me?
Yes, I understand.
Yes, in which case there's a sequence. Your second pick depended on the first pick. Your third pick will depend on the second pick because you were not shuffling the cards after each selection. So it's not random. You agree?
Yes.
Okay. Okay. So the very first thing we need to see when you get a set of numbers, the first question we want to ask is, are they random? If the answer is yes, then we say they are white noise. That is, if they satisfy the randomness condition for white noise, we say they are white noise. So a white noise process is like this, all these 8 numbers happening together. Okay, if there's no plan, this 3 that you selected for 1992 in itself was random for 19, was just one possibility out of infinite possibility of numbers for 1992. This 4 is just one possibility out of infinite possibilities for 1992 and 1993, all these numbers. If there's no relationship between this 4 and this 3, nothing, no plan, no interaction, no coordination, no no correlation, no contagion, nothing, we say this whole process is a white noise. Okay, guys?
Got it.
Okay. If it's not a white noise, then maybe Lily played a game, because when she took the first one and then she put them back, when she grabbed all 8 and then she was putting them back, maybe she flipped a couple of them but left the others the same, so that the next pick that she picks, some of them will be the same as the previous numbers, the other ones will change, and then she returned them without shuffling again. So the next pick, so in other words, from this set will be related to another set, will be related to another set, and so on and so forth. And if this number has a relationship with this number, with this number, with this number, with this number, then, hey, they are not white noise. Are you with me? Question: if they are not quite white noise, then what are they? Can anybody answer this question? If these numbers are not generated as a white noise process, then what was generating them? What kind of process can they be?
Arch, J arch, whatever you said. Those type of processes.
They can be hundreds of thousands of processes. They can be anything. Yes? They can be anything. So it's just like me asking you if a distribution is not normal, right? What kind can it be? Can somebody answer that? If a distribution is not normal, what else can it be? Well, it can be T distribution. It can be uniformly distributed. It can be binomially distributed. It can be any kind of distribution if it's not normal. You agree, right?
Yes.
Okay, good. But we have noticed that if a time series like this is not white noise, then it can be linear. The process generating it could be linear or non-linear. I want that to sink in. If this process is not white noise, then what else can it be? It can be linear. What do I mean by linear? This y equals a plus bx. But because we're dealing with only one series, it can be a plus b times y, previous y, last month's y. Or it can be a plus b times y 2 months ago, lag 2, and so on and so forth. Why do I call that linear? It's a plus b stuff. That's a linear model. But the most fundamental time series is the white noise. And when you make it Gaussian, that is when you make the white noise IID and normally distributed white noise, then we call it a Gaussian white noise. And just like the normal distribution is very useful to us because we need only two things, the mean and the variance. The same thing, the Gaussian white noise is very useful to us because we need only the mean, the variance, and maybe the autocorrelation, because this is a joint distribution. We have eight variables here, and we combine them together. So our problem in time series is, if first you get your data, you test whether it's white noise. If what is generating is not random, it's not white noise, then we ask, what else can it be? Well, it can be one of two things for now, broadly one of two things. It can be generated by a linear process or a nonlinear process. We have noticed that in time series analysis, the most popular type of linear processes, are what we call, sorry about this, what we call ARIMA. ARIMA meaning it can be autoregressive. I'm sorry. It can be autoregressive. It can be moving average. It can be autoregressive. It can be I integrated, or it can be MA. Sorry, when I get excited, my typing becomes messed up. So it can be AR, it can be I, it can be MA. Look, I didn't discover this, because for many years, many people have been studying time series in econometrics and statistics before you and I were even born. So generations of people have been studying time series, and they have seen that when time series are not generated by white noise, then they could be either generated by a linear process or a non-linear process. But what do we observe? Even if they are generated by a non-linear process, we can transform the non-linear process to become linear process. So if you and I have just limited time, in time series analysis, we focus on studying linear processes. Because even if they are generated by non-linear processes, you can transform them taking logarithms from non-linear processes into a linear process. For example, everybody, can you see me here? If, for example, the series is, for example, y to the power of 2, y squared. Okay, so it's non-linear. How can I make this linear? I can take natural log. I can take natural log of y squared. Where is this? What is natural log of y squared? It's equal to
natural log of y.
Exactly. It's 2 times natural log of y. I just made it linear. So the original process is non-linear. I hit it with logarithm. I make it linear. So why waste you all's time? You guys, yes, you're very wealthy, but you pay tuition, and you want to just finish and get the heck out of Baruch College and go get that $1 million job. So why teach you linear, non-linear, why teach you different processes when I know that whatever the process is, if it's non-linear, no matter the nature of the non-linearity, I can always transform it into linear. Are you following me? So we just focus on studying linear processes. If it's non-linear, we transform it back to linear. We transform it to linear, we do the work, and then convert it back to its original form. That's why in Echo 4000, what kind of regressions were you doing? Ordinary least squares regression, ordinary linear regression. That's all you did in Echo 4000. Is that correct?
We did that with multiple variables as well.
Yes,
and also
but even if you did multiple regression, it's still linear.
No, we did logarithmic as well, and also quadratic.
Yes,
and cubic.
but okay, that's fine. So, but the quadratic and the cubic, I can linearize them. Yes.
Yes.
Exactly, I can linearize them. So in all cases, we just focus on studying OLS, the ordinary least squares regression, the linear equation, because I don't want to waste time teaching you quadratic, cubic, or teaching you. There are infinite possibilities. If the generating process is not linear, I linearize it, so I'm going to focus on linear. So the same thing in time series. The most popular linear time series models are ARIMA. Okay, it's just so general. And we call it ARIMA PDQ. PDQ. Wait, let me make it. ARIMA PDQ. Okay, ARIMA PDQ meaning what are the appropriate lags? Okay, so I say for the autoregression portion, what is the number of lags? And by convention, we use P for the lags for the autoregression. For the integrated, we use D. And for the moving average, we use, sorry. So you will never hear me say moving average MAQ. I'm sorry, you never hear me say MAP. It's always MAQ. I didn't make this up. That's the convention in this subject. So it's ARP, ID, MAQ. Because, okay, let me stop here. Does anybody have a question? No, okay. All right, so for tonight, I'm going to proceed with autoregressive models, okay? And then we're going to spend like a couple of weeks on this. All right. So what is an autoregressive model? It's like, you know, y equals a plus b times b times y t minus 1, t minus 1 plus, I'm sorry, plus, let's use w for the error, okay? W at time t. So here we are saying here that y at time t is equal to a plus, you see? Here I'm saying that y today is equal to some constant plus b times y the previous month or the previous day or the previous year plus this WT. And this WT for autoregressive models, we assume this WT is white noise. Okay? Is everybody with me? I want to know that you guys are with me.
Yep.
Okay. All right. Excellent. Now,
Professor?
what if I, yes, who's asking me?
It's Danny. Professor, I just had a quick question on the A is the residual, right?
No, no. The W is the residual.
Okay.
Think of W, the white noise error process. Think of it as the residual in your Echo 4000. So when we say white noise, we are really talking about residual, something like residual in your Echo 4000.
Got it. Thanks.
What was the property? What was the most desirable property for the OLS to be perfectly correct and perfectly working properly in OLS? Average of the residual is 0, right? The residual is homoscedastic, constant variance. Yes?
Yeah.
Yes.
Sir.
Homoscedasticity is constant variance. So in Echo 4000, you learned the nice property. What conditions must hold for your OLS regression in Echo 4000 to be perfectly correct? What conditions? The error term must be average 0, constant variance. The covariances should be either 0 or some number. And then there should be no multi-collinearity. X1 and X2 right-hand side variables should have no relationship with each other, and so on and so forth. So you can think of our white noise process as the residuals properly behaved, mean 0, constant variance, 0 autocorrelations, and so on and so forth. Now, everybody, please look up here and tell me what I have just done. Suppose y represents return to IBM, okay? What is the difference between these two models? This one, number 1, and this one. Now, wait, let me transform this. What is the difference between these two IBM returns?
One is white noise, the other is linear.
This one is white noise, and this one is white noise, and this one is a linear process. But that linear process it tells me that every day, the return to IBM is generated by a white noise to which I have added a linear process. And that linear process has a constant value plus B, another constant, times the previous values of the returns. Are you with me so far?
Yes.
Okay. Now, what is the relationship between these models? Hold on. Let me introduce a third one. Okay. All right. So let me go back here and do this. What is the difference? So this one is a what? It's a white noise process. Is that right? Zero mean
Yes.
white noise process. What is this second process?
It's a linear as well without the intercept.
It's a zero mean autoregressive process, right? And this one is an autoregressive process with a mean A, or we say it's an autoregressive process with drift. That A meaning is drifting up, A. And if A is minus, is drifting down, A. Okay. This is what we call this first one is called an AR1 process. Why did I call it AR1?
Because it has only one variable.
No.
I mean, has only one regressant.
You're confusing me. You're being too technical for me.
So it only has one variable.
You guys
That's how we used to call it.
the danger you guys always pose is that you always try to confuse your professor, and that's not a good sign. All right, hold on. Let me finish. Let me do something else. Plus C. Hold on. I know exactly where you guys are going. Y. Okay. What is this process?
AR2.
Aha. So now tell me why you're saying it's AR1 and AR2.
Because it has two Ys.
There's two time periods that you're looking at historically.
No, you haven't used the correct word. This one, today's IBM value depends on what? Yes, today's IBM value. Yes, T minus
Yes.
1. Is that right? That's one lag. Today's IBM value is determined by IBM's value yesterday, IBM's value two. So this is a 2-lag model. It's AR2. Are you with me?
Yes.
This one is AR what?
AR0.
AR0, correct. So AR0 is a white noise process. If that WT is white noise. AR1 meaning if you want to determine IBM's return for tomorrow, just look at IBM's return for today plus or minus something. If you want to look at for this one, AR2, if you want to look at IBM's return tomorrow, look at IBM's model today, IBM's return today, look at IBM's return yesterday, and some kind of combination of IBM's return today and IBM's return yesterday will give you IBM's return tomorrow. Everybody okay with me?
Yes.
Everybody okay? All right.
Yes.
Okay. So, guys, why do we call it autoregressive? Autoregressive.
Because it regresses around itself, but at a
Itself.
different
But what do you
lag.
mean by regress?
So, yeah, to explain.
Yeah.
Perfect. Perfect. I mean, you guys are so good. Is Lily still there, my buddy?
Of course.
Roxolana, you suddenly went quiet on me.
No, I'm here.
Yeah, okay, good. Where's Alec? Alec, I haven't forgotten you. All right, so don't mess with me as if I've forgotten you. And I'm looking for Joseph Bishopin is here. Nikhil, are you still here? Alejandra?
Yes, I'm here.
Oh, the big guy is here. Mr. M, Mr. I M, you're here. Excellent. So I'm happy. All right. I just saw you. Okay. So homework that you're working on now is we look at the distribution, the joint distribution. We're asking if it's normal. So you're going to do that this week and submit on Saturday. The second homework is I'm going to give you a time series and I'm going to ask you, is it white noise? Okay, so we're going to do that. So we are going to review that. You're going to do that for second homework. And then the next thing will be, is it an autoregressive process? Well, but there's a problem. If I ask you, suppose I give you this list of IBM's return and I ask you, is this an autoregressive process? Is it an AR process? Is that a complete question or it's an incomplete question?
AR1, AR2.
Exactly.
How many ARs?
Exactly. So if I say, is it an AR process? The next question will be, okay, if it is an AR process, then AR what? What is the P? AR what? Okay, is it AR0? Is it AR1? Is it AR2? Is it AR3? Is it AR4? Is it AR5? And so on and so forth. Okay? So for autoregressive models, for autoregressive time series models, we have to ask first, is it white noise? If it is white noise, then we stop. That's AR0. Done. So white noise, yes, you stop. White noise, no, Then what kind of process is it? Is it AR? Is it MA? Is it ARMA? Is it ARIMA? If you say none of those stuff, it is AR. Good. Next question, AR what? AR0? It can't be AR0 because we said it's not white noise. Is it AR1? Is it AR2? Is it AR3? And so on and so forth, okay? So we have a way of answering all these questions. We have many ways of testing whether it's a white noise process. I already did that with you last week and 2 classes ago or something. And then we're going to ask now, if it's not white noise, is it AR process? And there are many ways of figuring out whether it's AR process, because we have to look at its autocorrelation function. Now, somebody please answer me this question, because I know you guys know this already. If this series is white noise, okay, and I take the mean of this series and it's white noise, what do I expect the mean to be? 0. That is a 0 mean white noise. If I take the variance, it should be constant. Now, if I take the autocorrelation at all the possible lags, what must the autocorrelation at all the possible lags be?
0.
0 individually and 0 jointly. Yes?
Yes.
Okay. Exactly. So 0 individually at each lag, and then 0 jointly. And
Like,
we
not for the first lag, right?
No, for the first lag. No. You mean lag 0 or lag 1?
Lag 0.
Yes, lag 0, autocorrelation must be 1.
Yes.
Okay? And for lag 1 and so on, it must be 0, 0, 0 individually and jointly when we test it with Leon box and so on and so forth. Okay? If it's not, so we already know the pattern. And by the way, everybody hold on, let me show you from your textbook the autocorrelation function for a white noise process. Where is this? I found it. God damn it, where is it? Give me a second, please. All right, let me go down, scroll down. Where's your textbook? Right here. Okay. All right, so this is your textbook. This is page 50 of your textbook. Let me go to page 48. I think I noticed a white noise. Huh? Come on, don't mess with me today. Ah, there you go. This is, all right. This is from page 48 of your textbook, okay? So these are sample ACFs, autocorrelation functions for monthly simple and log returns. Simple returns, meaning price today minus price yesterday divided by price yesterday percentage. And then log returns are the log difference, like you guys are doing for your homework now, okay? So these are the 2 ways of calculating returns, either simple, just simple percentage return, price at time t minus price at time t minus 1 divided by price at time t minus 1. Today's price minus yesterday's price divided by yesterday's price. That's what we call simple returns. And then these are log returns. Look at their autocorrelations at different lags. There's something wrong with this graph because it says at lag 0, who was that, Roxolana? At lag 0, the ACF should be 1, okay? So that's a mistake here.
Yep. Wait,
Okay.
so that's a wrong graph?
It's a wrong graph. It should begin, this should be 1. Instead of 0, it should be 1, because at 0, we should have 0 here and have the autocorrelation at 0.1 here. Okay? I mean, you guys, you know this, so you should recognize. But look at, for simple returns, look at all the autocorrelations. They fall within the confidence bands, yeah? Yes?
Yes.
So statistically, even though these numbers, each of them is not 0, but statistically, each of them is 0 at 5% level of significance because they are within the bounds. Yes, you see that, right?
Yep.
So this is a white noise process. This one is also a white noise process. Because
But
look,
a couple of them are a little over though.
I know. Let's not.
Okay.
Wait, so for the log returns, the ACF also has to be 1 for lag 0, correct? Those two graphs are wrong.
Yes.
Okay.
Okay. So look, this one is slightly above, but this guy made a mistake. Let's not split the. Let's not. How do we say? Let's not split hairs here. Okay. Okay. Yeah. This one is a little bit above, but let's assume all of them are inside. This one too. So this is a white noise process. This is a white noise process. If it's not white noise and it is autoregressive, what will this graph look like? Aha. Next Tuesday or next Thursday, guys, your head will be spinning when I'm done with you, because I'm going to show you a proof of what the autocorrelation function will look like. For an autoregressive process, the autocorrelation at each lag, there's an equation for it. And I will show you that equation next week. I will derive it with you. It's like 7 pages of my beautiful handwritten notes. Okay, I will take you each step through it, and I'll give you the 7 pages of proof. But it's so fun. I had so much fun writing it up myself. Okay, now so look, if you ask me, what's my friend Lily? This is what the ACF of a white noise process looks like.
Got it.
Okay, Roxolana. Okay, everyone. Okay, now let me show you what the ACF of an autoregressive process, what it looks like. Okay, let me just show you the diagram. Next week, I will show you the proof. I will derive it for you so that anytime you see an autoregressive process, anytime you have an autoregressive process, you can calculate the ACF at each lag. Okay, because there's an equation. There's an equation. Hold on. I am looking for where I left the. Guys, just give me a minute, okay? I have a beautiful picture for you for what an autoregressive, the ACL of an autoregressive process looks like. Okay, I have it right here. All right. Let me show you. Okay, let me go to page 39. No.
Professor,
Yeah.
these notes look very nice and neat. Did you work on them?
I didn't write them myself. I just picked them up from the internet. I have so many combinations of so many things from the internet, but I don't, if I give them to you, it will simply mess you up because it will, it has all kinds of equations somewhere. But eventually I'll give you all these notes, okay? I'll give you all these notes, but I'll combine them because from one set of notes, it could be 200 pages. And if you look at them, your head will spin and you'll get discouraged because all kinds of fancy equations. But eventually I will extract the relevant portions for the class, put them together and give them to you, okay?
Okay, thank you.
So because the equations can be messy and I don't want you to I don't want you to get discouraged, because even I get discouraged. Believe me, I get discouraged several times, but I don't want you guys to get discouraged. Okay. So look, guys, look at this autoregressive process. This is an AR1. You understand why, right? Does everybody understand why this is an AR1 process? Because it's only one lag, yes?
Yep.
Okay. This coefficient is 0.9. Next Tuesday, I will show you, last class, I posted an Excel file where I use an OLS regression to determine the coefficients. So we can use an OLS process. But this is a particular for an AR1 model. This coefficient can take any value from 0 to 1 and negative and so on. But for an autoregressive process, we want the process to be stationary. Why do we want it to be stationary? Because if it is not stationary, then it can blow up in our faces. The distributions are changing every day and every month and every year. Okay? It's non-stationary. But autoregressive processes, the most well-behaved processes, are stationary. So we will always test for stationarity when we have ARIMA processes, autoregressive, moving average. We test for white noise, and then we test for stationarity. But I have not discussed the formal statistical tests of stationarity. I haven't discussed with you. I will discuss it in the next couple of weeks, okay?
Oh, Professor.
Yes.
What does the y-axis represent, and what does the x-axis represent?
Okay, this one here, right?
Yeah. Both. What do both represent?
Okay, this represents, the x-axis represents time. Okay, and the y-axis represents the returns. Okay?
Okay.
All right. So this is just the graph plotted over time. Now, for this particular process, AR1 process with the coefficient 0.9. Now, the coefficient can go from 0 to 1. If this, instead of 0.9, is 1.0, so that xt is exactly equal to xt minus 1 plus the white noise process, we say that's a random walk. A random walk is highly non-stationary, but we shall discuss that next week. And if this number is 0.9, is large, it is closer to a random walk than not. Guys, if this coefficient is 0, exactly 0, then this process is a
white noise.
It's a white noise. So an AR1 process can go from one extreme, white noise, to the other extreme, random walk. And a random walk process is not stationary.
So for the max coefficient is 1 in this for this?
No. It can be more than 1. It can be 1.5. If it's 1.5, oh my God, you don't want that to happen. It will blow up in your face. But if it's exactly 1, it's non-stationary, but when the coefficient is exactly 1, we have a name for that process. It's a random walk. If the coefficient is 1.5, so xt is 1.5 times xt minus 1, it's a non-stationary process, but we cannot call it random walk. Only when this is exactly 1.0 that we say it's a random walk, non-stationary, autoregressive process, okay?
Is it stationary if it's below 1?
If it's below, for stationarity, we want it to be below 1.
Okay, thank you. And if it's white noise only, is that stationary or that's not? That's
If it's stationary, yes.
If it's 0, it's stationary?
Yes.
Okay, thank you.
Okay. Now, guys, look at what the autocorrelation function looks like. How do you describe this this process? Is this white noise? No, of course not, because they are the autocorrelation at each lag. What lag is this, by the way? This first one, what lag is it?
0.
It is 0. And then for lag 1, for lag 2, for lag 3. So this autocorrelation function, it is declining exponentially. You see, this is what we call an exponentially declining process. And you will see why. Because next week, I will show you that the autocorrelation at every lag is equal to, guys, can you please hold on? I have a very important call. Please hold on, okay? Cigar. Hi, I'm in class. I'll call you right back after my class, okay? Give me 20 minutes. I'll call you back. Okay, bye. Okay, let me encourage you guys, okay? This guy that just, let me encourage you guys. This guy that just called me was my student at Baruch College. He and his wife met in my class at Baruch College. They got married, and I was invited to their wedding in Indians. So I've known him for forever. He's a multi-millionaire already. So when he was in my class and I was telling all of them, you know, all you guys in my Baruch College class, I give you 5 years after graduating, at least 1/3 of you will be millionaires. They say, ha, 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 professor, you're crazy. So all of you in this class, I'm telling you, 5 years from now, at least 1/3 of you will be millionaires. So one of them just called me now, okay? All right, so let me go on. So next, sorry for the digression, guys, but that was an important call. So I'll show you next week. Look, what is this thing, phi 1? Phi 1 is the coefficient. Are you with me? Everybody with me?
Yes.
Okay, so for an autoregressive process, AR1 process, the autocorrelation at each lag is given by the coefficient raised to the power of that lag. So for this process, this one, the coefficient is 0.9, yes? Yes?
Yes.
Okay.
Yes.
Okay. So at this lag here, lag 0, it will be 0.9 to the power of 0. What is any number to the power of 0?
1.
It's 1. At this lag here, lag 1, it will be 0.9 to the power of 1. So this is 0.9. Are you with me?
Yes.
At this lag 2, it will be 0.9 squared. So it will be 0.81. You see that?
Mm-hmm.
At lag 3, it will be 0.9 to the power of 3, and so on. That's why we say it's exponentially declining. You guys understand now?
Yeah.
I will show you the derivation next week. It's a very long, but a lot of fun. I will give it to you. I've written it all out. It's like 6-7 pages, my handwritten note. I'll give it to you. I'll go over it in class as much as possible. Okay, guys?
Sounds good.
I'm excited.
Okay, so there's another thing. So if you download a series like you guys did for homework, and you do many things, and you compute the ACF function, and it's declining like this, that should tip you off that it's an AR1 process. But AR1 process of how many lags? To determine that, we need something else we call the partial autocorrelation function, okay? I will explain all of that next week. Okay, let me stop recording and then.
The recording has stopped.
Oh my God, guys, now we are entering into the fun part of time series, financial econometrics, okay? So many things to study, but I'll try to focus in each class so that at the end, in the aggregate, when we are finished with an AR1 process, then I can give you guys homework. Go to Yahoo or go somewhere else, get the data and tell me, number one, is it white noise? No. Is it AR? Yes. AR what? Okay. Is it stationary or non-stationary? So at that time, you'll be able to perform all these tests. Okay. Good night, guys.
Thank you, Professor.
Thanks,
All right.
Professor.
All
Thank
right.
you.
By the way, the president is giving a speech tonight.